Let me start the webinar. Good afternoon, everyone. Welcome to the first session of our SuperTwin project webinar series. In today's session, our instructors will be presenting SuperTwin, a digital twin ecosystem tailored for HPC systems. SuperTwin is the outcome of the SuperTwin initiative supported by EuroHPC-GU. Before we start, I want to express my gratitude to each of you for joining us today. We have 3 instructors for this webinar session. We will be forwarding your questions to the relevant presenter at the end of each presentation. Please ask your questions via Q&A chat box. First of all, I would like to introduce our instructors briefly. Fatih Taşyaran earned his bachelor's and master's degrees in science from Sabancı University. Currently, he is continuing his studies as a PhD student at Sabancı University, where he has been for a year. His research interests include high-performance computing, parallel algorithms, and data structures and performance analysis. During the last 3 years of his studies, he has worked on SuperTwin project as a researcher. Our second instructor is Jose Antonio. He is currently studying to obtain a Master of Science in Electrotechnical Engineering at Instituto Superior Técnico in Portugal. He is also a researcher working for the INESC ID organization. His study and research topics revolve around optimization and performance modeling of various hardwares. He participates in the EuroHPC SuperTwin project, where he is responsible for performance modeling support. And today's last instructor is Osman Yasal. Following his graduation, he decided several years to private banking sector before transitioning to pursue a Master of Science program at Parkour Lab, Koç University. His primary focus lies in investigating the energy consumption of software systems. Currently, he has given support to the EuroHPC SuperTwin project. So I will stop my screen sharing and leave the floor to our first instructor, Fatih.
Thank you. I think you can see my screen.
Yes, everything is fine.
Hello everyone, and thank you for attending to this webinar. I am Fatih Taşyaran. I will start the webinar and we will present our work on SuperTwin with my colleagues Osman and Jose together today. So let's start. SuperTwin is an optimization and co-design framework for sparse computation. It consists of 6 partners from 5 countries. The aim is to develop a supercomputing framework for enhancing performance and energy efficiency in sparse computations. SuperTwin, which we introduced today, aims to create a coherent interface between other tools and data produced by other sparse partners. So at the very core of the SuperTwin, the idea is to create a linked data for supercomputers and the data collected from supercomputers. The goal of the linked data is to facilitate easier sharing, discovery, and integration of information across different domains by using standard web technologies and protocols. You are seeing the screenshot of the linked open data cloud. It's a project aimed at publishing various open data sets on the web and linking them together. You can see the nodes in the screenshot are the data sets and the connection between these data sets are reference to each other. So one user can query these data sets with cross-referencing to different connected data sets. SuperTwin attempts to achieve this for the data collected from different systems with different settings, especially for the performance data. In the historical development of the linked data and digital twins, RDF has an important place. The resource description framework is a standard model for data interchange on the web and has been a foundational to link data, enabling the representation of information in a machine-readable way that can be easily shared and connected across different websites. With the proposal of Jason LD in the early 2000s, the principles of linked data have been made more accessible to web developers, facilitating the integration of semantic data into the largely JSON-based web ecosystems. DTDL is Digital Twin Description Language. It is built on top of JSON LD, and the DTDL aims to create intelligent and interconnected systems that mostly made up of single board computers or telemetry reporters, or mainly for logistic systems and smart buildings. DTDL has proposed a good foundation for representing computers as digital twins, but it mostly aims static devices such as thermostats or or GPS systems, and this is not doable with the supercomputers or regular computers that we are using. In the regular computers, we are using the number of telemetry and the frequency of telemetries are changing very rapidly, and components are varying greatly between different systems. So, as using the digital twin description language as a foundation, we derived the SuperTwin knowledge base from digital twin description language. We added custom mutable interfaces and pointers to the digital twin description language and acquired the knowledge base of SuperTwin, which stand at the heart of every SuperTwin functionality. So what is SuperTwin? SuperTwin is briefly a digital twin framework specifically designed for HPC systems. It provides advanced visualization and actionable insights. On top of that, SuperTwin implements static and real-time performance models for accurate system analysis, which Jose will talk more in detail, and it proposes an abstraction layer to simplify complex system interactions, which Osman will explain in detail later. So, as a start, we have the SuperTwin library written in Python, and the environment variables such as address of the databases of the of databases that the system using, and some tokens like Grafana tokens, etc. We want to measure, visualize, and record the system's performance, which requires heavy tasks such as running a time series database, a metadata database, a visualization framework, etc. To this end, we have implemented SuperTwin framework to work on two different systems. One of them is the target system, and one of them is the host system. You can think SuperTwin as a binocular that look into a system. In our case, the binocular is the host system that runs the SuperTwin framework, and we are looking at the target system from a distance. Therefore, we want to cause a minimal effect on the system we are observing. To be able to do this, SuperTwin runs any heavy workload on the target system. Sorry, SuperTwin runs any heavy workload, such as the databases and visualization frameworks, etc., on the host system, and it runs only the samplers and applications of interest on the target system to cause a minimal overhead. SuperTwin functionalities are consist of different phases and scenarios. To be able to model the target system and generate its digital twin, we need to have in-depth information of the target system. SuperTwin runs a probing on the target system using widely available Linux tools. Target systems need to have these tools installed beforehand the probing starts, but since they are so common in Linux ecosystem, installation is generally requires only one liner. The SuperTwin piece its probing library on the target system, runs it, and copies the output of the probing back to the host system. After the probing is complete, we have the hardware specifications of the target system, such as the processors, disks, GPUs, network interfaces, their models, frequency, memory sizes, cache sizes, disks, network interfaces, and etc. We probe detailed topology of the target system, such as threads that share a cache, NUMA topology, and more. In short, we are collecting in detail information about every piece of hardware on the target system that have an effect on the performance of the applications that run on this system. And on top of the hardware component specifications, we are probing for every software and hardware metric that they can report. This phase generally takes 3 or 4 minutes. It is a lightweight test. Once we have the probing information of the target system, SuperTwin generates a knowledge base for the target system, which acts as the digital twin description. And we store this knowledge base in the MongoDB. This knowledge base is the sole parameter of SuperTwin library, and once it's generated, every other SuperTwin functionality is enabled, and we are keeping this knowledge base in the MongoDB. And once the SuperTwin object, which is created in Python with SuperTwin API, wanted to be used one more time or wanted to be scripted, we are getting this knowledge base from the MongoDB, and we are skipping the probing phase, basically. But on top of skipping, this knowledge base is grows with every usage, and the sampled metrics, sampled data from the target system is encoded on the knowledge base in a structured manner. This is a simple as abstraction of the knowledge base. This is the most basic version of a knowledge base. The knowledge base is the main data structure of the SuperTwin. It includes meta model classes, interface from digital twin description language, and its derivatives, which are mapped to components. On top of the interfaces, it includes property, relationship, and telemetry entries, which used to describe capabilities and relationships among entities. Altogether, they make up the knowledge base, which we can briefly capture any information about the target system. So in our knowledge base here, we have levels of the target system. We are abstracting the target system and generating this graph architecture with the knowledge base. We have levels of the nodes, which are the interfaces that are mapped from the target hardware. We have a system level, socket level, core level, thread level, and cache level nodes for any target systems. And once a user wants to uh, investigate a performance anomaly or a performance behavior or an application's behavior, they can start from any of these nodes and traverse the knowledge base graph structure as they want, and can acquire the information from the target system, going from general to specific or specific to general, or a user can go horizontally and compare different components from a system or different systems, or user uh, can go vertically to have a general picture of the target system. So here we are seeing some properties and telemetries that are belong to different levels from the knowledge base. We are seeing here the some contents of the system interface, which is the most general interface below the cluster level knowledge base. In our system interface, we can have properties like OS of the target system or the microarchitecture of the target system. For example, this system has an Ice Lake processor, or we can have software telemetry of the target system that is about the whole of the systems, such as the uh, CPU idle, the augmented CPU idle of the whole system. This system interface, apart from the hardwares, the memory subsystem and the processor hardwares, it contains other hardware that is exists on the target system. This could be the disks on the target system, the network on the target system, the GPU or other devices at the target system. It can also model processes as a part of the target system. This process interface is a uh, real-time mutable version of the regular interface. It captures the process ID of the processes on the target system. It can change the process ID of this process interface entry once a process on the target system change its process ID, and it can also collect per process metrics from the target systems with this way. All of these interfaces and devices are under the system level. Uh, Next to the system level, we have socket level interfaces. In our socket level interfaces, as the name suggests, it is the properties and telemetries and hierarchical relations that is about a socket on the target system. Of course, it can capture the normal topology of the target system, and each socket have their own subtree in the knowledge base. In this way, we are seeing the model of the processor that socket have in this example. We can have information like maximum frequency of the processor. We can have software telemetries from the operating system that is related to the socket, such as the NUMA memory that this socket is using from its own domain, or we can also have a PMU telemetry or hardware performance event telemetry that is related to this socket, such as off-core requests. At the core level, we are keeping the relationship entries because the hardware performance metrics are generally reported from the threads, not cores. But in this way, we are keeping the threads that share the same core, and we are keeping the threads that share the same cache. And with this information, we can launch applications in a cache-aware or memory-aware way. At the thread level, we can again have software telemetry data like CPU idle from each individual thread, or we can have a PMU metrics for each CPU thread on the target systems that are directly related to the systems, to the applications that run on the target systems. The number of metrics we have probed or could be sampled with this way is generally in the order of thousands. Sorry, 1 second, please. In the cache level, we have the cache-related metrics for each individual cache on the target system. That is not a generalized sampling or modeling. Each individual cache on the target system have their telemetry and PMU metrics sampled with their own address and with their own interface. With this way, we can isolate caches from within systems or from within different systems and can analyze them individually. The modifications we make on the DigitalTwin description language is the structure and the generation of this knowledge base and the addition of the parameters for the other frameworks, other third-party tools that SuperTwin manages for the target systems. SuperTwin at the moment manages Perf utility from Linux, Performance Copilot, InfluxDB, Grafana, and MongoDB in combination with each other. SuperTwin integrates all of these frameworks into each other, and to be able to do that, SuperTwin on top of the name of the metrics and properties and topological information, it keeps the aliases and or we can say parameters to configure these frameworks to sample or query these individual components. It adds these parameters to each of these individual entry of individual hardware, and with this way it can individually sample or isolate or link the data of different components with each other. This is an example of how the SuperTwin generates a visualization for the numerous hardware components for a target system from going from general to a more specific for a target system using its knowledge base. And also, this is how SuperTwin executes its probing phase and generates the knowledge base for a target system. To start the SuperTwin, using the SuperTwin implementation in Python and SuperTwin API, user only needs to enter the IP of the target system and a username for the target system to SuperTwin, and then SuperTwin handles the rest of the operations automatically and generates a twin description for the target system. This is, of course, speeded up a bit. Some pre-scripted applications could be run just after the creation of the SuperTwin as observations. Here you can see the twin document is created and added to MongoDB. And these are the entries for the knowledge base for different components of the target system. So after the creation of the knowledge base, we now have our parameters to manage different frameworks to monitor or observe different components of the target systems at the end. And now we can start to use the functionalities of the SuperTwin. At the first scenario, we can set up samplers to sample software metrics from the target systems for the entirety of the target systems components, and we can generate a dashboard automatically, again using the parameters from the knowledge base for the target systems. We are, while doing this, we are using the InfluxDB to push the time series data. We are acquiring the target system and correlating the data we collected in InfluxDB with MongoDB, again with the parameters added to the knowledge base. When a SuperTwin is run against the machine, this monitoring dashboard is generated automatically, and address of this dashboard is added to the knowledge base of the target system. When we run an application on the target system, we can see the effect of the application on the load that is created on the target system. We can see the frequency of individual threads along with this topological information. For the target system, we can see the number of processors, number of users, and next to the energy, real-time energy used by the target system, and information like temperature. But this is in this monitoring dashboard, we are mainly sampling software metrics from the target system. That metrics are generally related with the system state of the target system. So with this information, you can detect a thermal throttle or a memory eating process, etc. But the SuperTwin have another mode of sampling, which is the high frequency sampling with uh, a application that is launched by SuperTwin. In this mode, SuperTwin launches another sampler for the application that could be set up with the metrics the user wanted uh, previous to the launch of the application. After the launch of the application, SuperTwin generates a thread affinity for the target system. It have different modes, for example, NUMA compact, NUMA tight, or compact in non-NUMA systems. And on this prepared affinity, it creates a thread binding for the target systems. It runs the application. It samples the previously set metrics for this application and record the it pushes the time series data to the time series database and record the results in a structured manner in the knowledge base. This is the information observation interface. Observation interface is a formula to be able to query the data sampled during this observation for a later time. But before the launching of the observation, uh, as I said, SuperTwin reconfigure the samplers. It generates the configuration for the sampler. It generates a script to set affinity and launch the application on the target system. And while executing the generated script, it samples and creates an observation interface for this performance event. After the completion of the executed application, it generates an observation interface that we just see and appends it to the knowledge base at the MongoDB. It can also execute benchmarks and create benchmark interfaces on the target system. And Jose will talk more detail about this topic. This is a visualization that is generated leveraging the observation interfaces that are created for the applications for a system. SuperTwin can launch multiple applications on a target systems or can launch the same applications with different inputs, different orderings, etc. And can compare the sample data on the run automatically using the information in the knowledge base and can generate dashboards and that overlaps the data that are sampled as they happened at the same time. With this way, a user can see the program phases or the input orderings effect of on different performance events. As I said, these observation interfaces and knowledge bases are interactable with each other, just like the open linked data project. Our data from different systems are completely interactable with each other, that are cross-referenceable with each other automatically. With this way, SuperTwin can generate queries and can generate visualizations on top of these queries for the application executions that take place on different systems and at different times, and can also overlap these readings and can provide the user with the program phases and effect of the architecture changes or the input changes on the performance on the application. Again, in this example, we have Dolap, RCM and random, and Fedora RCM and random results. These Dolap and RCM, Dolap and Fedora are different machines, and we are having their sampled hardware performance events visualized on the same dashboard automatically. At this dashboard, SuperTwin can also generate augmentations on the sampled data and can compare them with different visualization options. So to assess the credibility of the framework we implemented, we have measured the resource usage and overhead and the accuracy of the sampling metric readings we made on the target system. You can see two different systems again here. The ICL is an ice lake machine, and say SKX is a Knight's Landing machine, if I am not remember if I remember correctly. The difference here is SKX is a high-end server with 88 threads and 1 terabyte RAM and with multiple users, etc. ICL is a personal server, a high-end machine, but it has a smaller scale. What we can see here is the resource usage of the SuperTwin with the most relatable cases. For example, this is for the software metric sampling together with hardware metric sampling. With the most relatable cases, just as frequency, one report per second or two reports per second. We can see here it uses only a fraction of a single core in almost all of the time. Its memory usage doesn't change with increased frequency. Its memory usage doesn't increase with a bigger machine, and network usage is scales well with frequency, and in general the resource usage is negligible for the target systems. Other than this, we have measured the accuracy and overhead of the metric readings we made. In the error part, we have found that for the metrics, we can got the truth value for applications. We see errors between 1 in 1,000 and most of the time less than 1% for the metrics read differ from the truth value, and this is enough for generating performance models for the target systems. And in the overhead, we see that the overhead, our metric readings score is generally around 1 in 1,000, and in some cases it is negative actually, but this is also reported from other works. this is most probably not negative, but it is so negligible that sometimes it is smaller than the natural variation between the runtimes of the same applications at different times. SuperTwin is progressing into a performance database to collect and correlate more data to facilitate architecture research and algorithmic research. To this end, we have a global performance database. In this global performance database, we are collecting knowledge bases and observations interfaces together with benchmark interfaces of different systems. And this performance database can make different systems data available to each other and can make data available to each other and facilitate users with the link data with the more than one system and other users systems. This is a screenshot from our performance database. You can access the SuperTwin from GitHub, and you can access the documentation in read the docs. And that was the end of my presentation. My colleague Jose will continue with the performance models.
All right, so I'm going to go ahead and share my screen. Okay, so I think you can see my screen now, all right?
Yes, that's fine.
Okay, so hello everyone, I'm José Morgado and I'm from INESC-ID, and today I'm going to be talking more about the CARM and GPU related features of SuperTwin. So starting off with the CARM, which is the cache-aware roofline model, a performance model that we have in SuperTwin. First, I would like to introduce it. So the CARM is an easy to understand performance model, which can give you an accurate performance overview of your application for a particular system. And it provides you with some good optimization hints that will help you prioritize your efforts in the right direction to achieve some better performance on your applications quicker. But first, how does it work? So the CARM has two main roofs, as you can see on this picture. We have some sloped roofs in red, which are dictated by the maximum bandwidth of each memory level of your system. And then we have a flat roof in blue, which is determined by the maximum floating point performance of your system. And these roofs then define two areas below them, which are the memory bound area, the red one, and the compute bound area, the blue one. So in this case, usually we plot your application in this graph, and the positioning of your application will let you know what you need to do to improve your performance. So for example, if your application is in the memory bound area, like this first green dot here in the graph, you need to improve first some memory access related parts of your application. So things like improving memory access patterns, data transfers, or your cache usage, for example. Then you can also have your application in the blue part, which is the compute bound area. And here you need to improve your utilization of the arithmetic units of your CPU. So things like using vector instructions, parallelization, among other things. And finally, you can also be present in this mixed area. And in this case, your application will probably benefit from both strategies to improve performance. So this is kind of how you read the CARM model. So then how is it constructed? So the CARM will always be tailored to the underlying system that it's drawn for. And this is because the CARM is actually constructed based on some data that we obtain from empirical micro benchmarks that we run on the system. So these benchmarks are designed to fully exploit the different features of your system in this case, the achievable memory bandwidth and the maximum floating point performance. And this is done with some memory micro benchmarks to target each of the memory levels of your system. And then a floating point micro benchmark to measure your peak flops of your system. And to automate this process, we have the AdCarm tool, which is a tool responsible for generating the micro benchmarks, running them, and measuring their performance on your system. And this tool is actually integrated into SuperTwin, which is why when you run SuperTwin, you are also able to get a CARM graph for your system. And this feature is fully integrated, so you can, when you launch SuperTwin, you can choose to have the CARM graph drawn for your system, and everything will be taken care of. And so, because SuperTwin has some live monitoring features that allow for a very big flexibility in the sourcing of metrics, we can actually make something that combines the static results of the CARM micro benchmarks and the live reports of your performance units of your computer. So, for example, we are able to do this live CARM dashboard, which will be generated for your system with SuperTwin. And this live CARM dashboard contains the two main metrics of the CARM graph, which are arithmetic intensity and the performance in gigaflops. And this allows you to plot your application's performance in real time in the CARM graph, so you can take advantage of the various tips that the CARM graph gives you just by visualizing it. And this can be very useful for some heterogeneous applications, which can have different execution phases that can result in different bottlenecks at different approaches. So this is basically supported by Grafana and conjunction with PCP to source the performance metrics. And the static CARM lines themselves, the lines you see in blue, they come from the results of the micro benchmarks that the AdCarm tool runs on your system. And besides support for x86 CPUs, we also have support for ARM CPUs in the works with some tests that include Scalar and Neon SIMD benchmarking. However, the live version is not very much ready yet because we have problems calculating the CARM metrics with the available metrics of ARM systems. So this is still in the works. So next up, I'll show you some possible use cases where you could use the live CARM. So these could be things like application analysis and benchmark validations. And for the example of application analysis, we ran here two different SPMV implementations. So we have Intel MKL SPMV in pink and the Merge SPMV in orange. And this was run on original matrix, and then it's RCM reordered version to also observe the improvement that we get by reordering our matrix before running SPMV. So as you can see from the graph, you can see right away that the Intel MKL performed better than Merge. The dots are placed above it. We have more gigaflops, more arithmetic intensity overall. And this is mostly because Intel MKL SPMV was actually able to use AVX512 instructions from the CPU that we used to run this on, while the Merge SPMV only stuck with scalar instructions. But besides this comparison between the algorithms, you can also see that the RCM matrix in green always outperformed the blue matrix, the original one, when running the same algorithm, which shows us how reordering the matrix can help the performance of any of these algorithms. So this is something you could do, for example, for your own application to compare different versions of it and see how your performance improves with your changes. And then for another example, things like benchmark validation. In this case, we ran some benchmarks from the Liquid benchmark suite. And these were the peak gigaflops, the DDOT and Triad benchmarks. And the particular thing about them is that they all have a predetermined arithmetic intensity level, which means that when we run them on our system, we should get a similar reading from the live CARM, which goes in line with what you can see in this picture. So the different colored X's represent the theoretical arithmetic intensity of each of the benchmarks. And as you can see from the dots in the live CARM, they are pretty much spot on. So this shows us how the live CARM can still be very accurate, even if handling live data. And another particular thing is, for example, the peak gigaflops benchmark, which is meant to fully take advantage of your floating point performance. As you can see, it reached our measured limit for floating point performance on this system, just like our CARM micro benchmarks measured, which also means that our limit measured with our micro benchmark is actually also quite accurate. So you could do this for your own benchmarks if you are trying to fully exploit your system. This is a good way to make sure that you are actually reaching your limits. And now, as a possible future feature, we are also working on a memory curve graph that could be generated for your memory system. So this consists of the bandwidth measured on your system for different problem sizes, which can give you a good idea of, for example, cache sizes and how your bandwidth will scale depending on the size of your problem. And this this is working for x86 and ARM, but right now we do not have the full integration yet with SuperTwin, so this is still in the works. And now I am going to show you a small demo of me executing some applications on the live CARM dashboard. So this is what you would see on your own system. When you run SuperTwin, you will get your live CARM here. And down you can also have some different metrics sampled for you. So for example, we have scalar double here, AVX2, which is called 256 double, and total memory operations, for example. And here, what I'm going to do in this small demo is run some different benchmarks. So right now, as you can see, we have some dots there that represent basically my idle system. So because this is on a local computer and running a screen recording, we have some activity. But now what I'm going to do is, for example, run some benchmarks that will stress my floating point units and my DRAM bandwidth. So these particular benchmarks will target the memory level of the DRAM. And for example, if this were your application and you wanted to improve your gigaflops counts, in this case, first you would probably consider going with some scalar instructions. And what I'm going to show in a second is that I'm going to switch off my benchmark that was measuring scalar floating points, and I'm going to switch to an AVX2, which should now result in the dots moving quite up. So as you can see right now in the new square that showed up, we are doing now AVX2. Sorry, and this results in much better floating points per second. And for example, here on our live metrics, you can see that the scalar doubles stopped and the AVX2 doubles have started being counted. So this shows you right away with very good precision that it's being sampled every second here in this example. And then, for example, if you wanted to change, I'm going to now change from DRAM to an L1 benchmark, which should move our dots all the way to the left, because we are going to do a lot more memory transfers, but keeping our floating points the same. So what's going to happen is our arithmetic intensity goes down. And as you can see, as soon as I switched from one to the other, we can have our dots here. And we do not reach the maximum performance here because this is done on a local machine while also having the noise of doing the screen recording. It takes a toll on the performance. But this is kind of an idea of what you could expect to see when running different benchmarks. And finally, I'm going to stop these benchmarks and I'm going to run the SPMV implementation that I talked about earlier. So I'm just going to run the Intel MKL here in a second. So I'm going to do it for a matrix and then for the reordered matrix, and you will see right away the difference that the reordering can make on the performance. So I just started up the regular matrix SPMV, and now our dots will show up in just a moment. Here we go. So as you can see, the new dots have moved over here. So in blue, we have the original performance, and here in red, we have the transition phase. So basically this SPMV algorithm first has a transition phase where it reads the matrix and converts it to particular format to then execute SPMV. So that's the result for those dots. But as you can see, while it runs, new dots are being formed inside the blue box, which basically corresponds to our average performance. And now what I'm going to do is switch off the original matrix and start with the RCM version of the same matrix. And we will get some new dots here that will show us how many more flops we can get and a better arithmetic intensity too. So as you can see, our new dots now show up over there. So we had about a twofold increase in our gigaflops and a slight increase in arithmetic intensity. And in this case, this was actually so fast that the SPMV finished executing, and we also had the report from the program that measured an average gigaflops of 1.36. And as you can see here in the live CARM, I don't know if you can read very well these numbers, but basically our axis is pointing as the dots are around the 1.30 range. So even with the system noise, our gigaflops calculations were quite accurate, quite on point. And so this is one example how you could do. You could use the live cache aware offline model for your applications by trying out different inputs, different versions, and seeing right away if you improved your performance or not. So now I will move on to some other features, the GPU features. So these consist CUDA kernel profiling and live sampling of performance events. So the CUDA kernel profiling is achieved by interfacing the NVIDIA Nsight compute with the SuperTwin framework, and finally by displaying the results in Grafana dashboards. And then the live sampling of the performance events is supported by a new extension of the Performance Copilot, which allows for the collection of live performance events from NVIDIA GPUs, which we then also display with Grafana. So for example, here the kernel profiling, thanks to NCU, we can sample various metrics from the execution of our kernel. So this is not live data, but this is the cumulative results of running our application. And we can then display them for you in a Grafana dashboard with different metrics that you want. And this is done by SuperTwin interfacing with NCU. It generates wrappers around the execution commands and sets up NCU to profile your launched kernel. And then it parses your results and adds them to the knowledge base as an observation interface, which then can be shown in Grafana. So for example, here we have some metrics that you can sample, like the DRAM to L2 traffic, L2 to L1 traffic, and floating point operations of different precisions, and then different throughput percentages. And then we also have the live performance sampling, which is thanks to the Performance Copilot extension that introduces some GPU-based performance events for NVIDIA GPUs. So SuperTwin can now collect and display these events in real time, similarly to how it does for CPU events. And this means we can also do some custom metric calculations that are derived from the GPU-based performance events. So this can be a good option to monitor your GPU application live and visualize your different execution phases more easily. So for example, in this panel here, we have the live free, used, and total memory of the particular GPU of the system that was being monitored. And so this basically concludes the different ways you can monitor your GPU and your GPU performance with SuperTwin. And it also concludes my part of the presentation. So now I'll pass on to Osman to continue this part.
Yes, thank you, Jose. Let me share my screen very quickly.
Go ahead.
I believe you all can see it now.
Yes.
Okay, so I'm going to talk about the PMU monitoring feature of SuperTwin. This is actually important because almost many of the things that you saw at Jose's presentation are actually built on top of this feature. So for people who doesn't know much about performance counters, I have a very simplified view of a CPU with performance counters here. As you can see, a CPU has clock caches, config register, branch predictor, and a pipeline, and actually the many others. And if you think that performance counter is at the center of the CPU, you can get the idea that many events happening inside the CPU, inside caches, pipeline, branch predictors, etc. And the performance counters are responsible of counting those events. For example, how many cache misses you have, how many mispredictions you have. So by using those events, you can actually classify your application into a sub area and determine where your application lacks of. So programmers can tweak these performance counters to count some different events based on their preference. So we wanted to give this feature to SuperTwin, and SuperTwin can now also configure and monitor these performance counters of CPUs. Technically, based on the microarchitecture, you can monitor 4 to 32 events simultaneously with high accuracy, but this is depending on your how performance counter is actually implemented in. Monitoring and configuring these counters are not as easy as configuring the other metrics, because I mean, we have some common events such as cycles inside clock or instructions being carried out, but there are some events that changes from a microarchitecture to another and from a vendor to another. For example, Intel may support an event X, but that event may not exist on AMD side or vice versa. And even though there are some events that give you the same thing, their names might be different. For example, I have instruction retired on Intel side. However, the same event, the same thing, is retired instructions on the AMD side. So this is a bit of a problem, because as the target system that SuperTwin monitor changes, you have to also change these events based on the target system. So to cope with this issue, we provided an abstraction layer on top of this PMU hardware events. Since we don't want to monitor all the events, we created a bunch of events that we are mostly interested in for our future work. So here, for example, Ripple energy, floating point operations, branch operations, and cache hits and misses. We created those made-up events, and we manually mapped these events to actual PMU hardware events. So in the big scale, we have different target systems here: Intel Ice Lake, AMD, Intel Sonico, and I have SuperTwin here. What we do is we fetch the DigitalTwin information, this knowledge-based information from our database to figure out what the target system is, what its PMU brand is, etc. And then by using our defaultly monitored events, which is these made-up events, we map those to actual hardware events, and we create a dictionary here. And this SuperTwin uses this dictionary to configure target systems to get the default events that we want. So, but in the meantime, it creates this configuration file based on the target system. The context of these configuration files are highly different, but they all, at the end of the day, gives us the same thing, same measurement. So we implemented this for Intel Cascade Lake, Intel Ice Lake. On Intel side, on AMD side, we implemented for Zen 2, Zen 3, and Zen 4. And for ARM, we are starting supporting this ARM CPUs as well. So in the programming side, what we do is actually we have this PMU mapping utils utility. The general idea is to put the PMU name here as a parameter, and for the second parameter, put the generic name of the event that you want to monitor. And this Python script returns you a formula saying that on that target system here in this PMU, if you start monitoring these two events, for example, data cache refills from system, LS, LCL, DRAM, etc., and add the results up, you will get this generic event. And this formula changes from system to system. And of course, you can use the SuperTwin object itself directly without giving the PMU name, because since we already have that, you don't need to put that here. You can directly call that, like, you know, SuperTwin dot get for PMU formula for total cache miss. So I have a video here. The takeaway of this video is I'm going to start SuperTwin for a random target system, and I expect that to configure the PMU counters of target system such that it can report my generic events. So let me just speed it up a bit. So I started SuperTwin for this given ID. And then it configures the target system and configures the PMU. This is too much. So once I open up the dashboard, I expect to see the generic events that I want to monitor. So here, I stop the video. As you can see, I have total memory operations, retired instructions, floating point, retired operations, and this is goes on and on. So regardless of the target system, we can configure a target system to feed these generic events data. So that was my part. Thank you for listening.
All right, so do we have any questions?
Yeah, we can start the Q&A session now. If you have any questions, please use Q&A part to ask, and then we will be happy to answer.
Well, if not, we can wrap up, and if there are no questions, just to make sure.
Let's
Okay.
wait a few minutes to wrap up. I think we have one. What's
Yes,
your
yes.
experience monitoring larger system larger than simple kernels?
Go ahead if you want to ask a question.
So, do you mean applications like MPI applications, distributed applications? We had preliminary results on the sampling on distributed applications, and the overhead is still in the border of being negligible. So we can say that it stays negligible for until a very sizable application. There are also other work on the literature on this issue, and they have also reported that the overhead stays negligible.
One more question.
Hı hı.
Question is that if your monitoring infrastructure has a failure, does that stop jobs running or executing correctly?
It does not stop the jobs, but it immediately restart the monitoring infrastructure. The samplers can crash or have fails time to time. If it happens, it just kill the process and launch the new samplers in a time of 1 or 2 reports. You're welcome.
Is there any more questions? Okay, there is no any questions in the Q&A box. So we would like to thank all of you, the participants and presenter, for being here today. And we look forward to seeing you at the future events. And the future events link on the chat box I just put over there. And the next Sparse City webinar will be on Sparse Base and Sparse Viz on March 7 of the next month. You can find more information about webinar and registration form on Indico event webpage, which is on the chat box. Thank you for all again.
Thank you.
Thank you for listening.
Thank you for listening.